Everyone, welcome to the Ask Mayfield Anything for February. We're going to get started in a minute here. We'll let more people sign in. All right, we are very excited to start this Ask Mayfield Anything. Again, welcome and thank you for joining us. There are still quite a few people logging in to the webinar, so in the meantime, will go over some housekeeping things. I'm sure everyone is very familiar with Zoom at this point, but just a reminder, at the bottom of your screen, there should be a menu bar and there's a little Q&A feature. So throughout this, feel free to submit your questions using the Q&A feature. And we are going to be answering questions live. We'll go through the topic for today, and then we might answer questions throughout the discussion, and then we'll answer most of the questions at the end. And then throughout, we will be sharing some links here and there, and those will get posted in the chat. So just remember, chat will be for links. Questions, keep them in the Q&A section so I can keep track of them and answer them. And with that, we will get started here. So my name is Jennifer Alfsom. I'm the Director of Business Development for Mayfield Renewables. I've been in the industry for 10 years, and my background is as a mechanical engineer. I used to design roof mounts back when Quick Mount PV was still its own company. And I've been with Mayfield for the last 4 years doing technical consulting. So things like helping clients with creating white papers, technical blog articles. The way I like to describe it is bridging the gap between engineering, marketing, and sales. So that's what I do now. And joining me is my boss and our leader of Mayfield Renewables, Ryan Mayfield. And he has been working in renewable energies since 1999, founded Mayfield Renewables in 2007, and his career has blended technical expertise with an affinity for writing and education. He has a limited renewable energy technician license in Oregon and is that still current on the Oregon Solar Energy Industries Association, the OSEA board?
As of last Friday, I am no longer on the board, so.
So it's a 3-year run, right?
3-year run that just finished on Friday, yep.
Wow.
Yeah.
Well, OSEA was lucky to have you, and I think one of our very own will hopefully be taking your spot, but we'll see if she wins the election.
Yep. So thanks for thanks for the introduction and welcome everybody. I also just want to take a quick second and just recognize Jennifer, Christy, and Lucas on our team who really do the majority of this work and put this together. So thank you to all of you for all the hard work behind the scenes that make this look so good and seamless. So, and welcome to our guest, Rick.
Mm-hmm. Yes, thank you. Christy and Lucas, our behind the scenes team. And let me welcome our guest, Rick Irvins, president of Pure Power Engineering. So he leads the team of engineers that has designed over 1,000 C&I and utility scale projects since 2012. Rick has been designing solar projects for 12 years and also has many years of experience of solar installation and O&M. He uses that experience to improve his designs. Rick also holds a master's degree, several master's degrees and licenses, including a professional engineering license, and is also a licensed electrician. So thank you for joining us today, Rick.
Thank you very much. Glad to join.
I should have asked you this while we were prepping for this. Did I get your last name right? Irvins?
Yes.
Okay, great. So today we're going to be talking about the concept of free voltage drop. So I think everyone's pretty familiar with voltage drop, but this concept of free voltage drop was actually written about in a blog article that Pure Power Engineering put out. This AMA is going to be a little unique because we actually have two topics that we're going to dive into today. We're going to talk about that free voltage drop, and then we're also going to get into discussing 1500 volt design recommendations. And then there's another blog article that speaks to that. But let's start off with voltage drop. So talk to me about the concept of free voltage drop. What are we really discussing here, Rick?
Sure.
Oh, are we starting with design? Oh,
yeah, let's start with this one. Yeah, let's start with the 1500 volt inverter.
Okay.
Yeah, and this here is the top of our blog article on our website that you can check out later, as well as I have it on the link. And got an image on the next slide. So that article really goes into the three major categories of ways to lay out your ground mount site. Could apply to rooftops too, but we'll really talk mostly about ground mount here. And the first of the three options, that's a good one, is where you have your string inverters distributed throughout the array. So if you got a bunch of rows of solar panels, you can put an inverter distributed throughout. So you got one for these 3 rows here, then a little further down, you put another inverter for those 3 rows, a little further down, another inverter there. And what that ends up doing is making your DC runs really short because it doesn't really go far outside of the array or that row before it switches over to AC. And you end up with longer AC runs that may run to a panel board to a switchboard, then to the transformer. So you end up having short DC and long AC. This seems to be the default for many in the industry over the years. And I think that's because when string inverters first came out, they were really used first on rooftops. And with the rapid shutdown requirements coming up in the NEC, that 10-foot from requirement in 2014, that really made people want to spread these inverters out through the array, because if you have it right next to the array that's being fed by, that also addresses the rapid shutdown needs of the time of that NEC. So then once string inverters kept getting cheaper, people started using them then on the ground mounts in place of central inverters and thought to apply the same as the rooftop. Let's just spread them all throughout without really thinking that ground mounts should be designed a little bit differently since we don't have that rapid shutdown requirement to take into account. And so like all arrangements, you got some pros and cons here to this particular arrangement. If you want to do the next slide. So some of the pros, the first one is you can eliminate combiner boxes with this. A lot of string inverters have that combiner box built in. The fused inputs are right there below or on the side of the inverter. You don't need that extra component that you need to purchase and install and wire up. So that's a benefit here. Some string inverters don't have this, and it all depends on how you spec it out. We'll talk about the other type a little bit later. And of course, if you don't have that combiner box and you're going straight into the inverter, odds are that inverter also has multiple power point trackers, whether it's 3 or 6 or more different power point trackers. So when you have a combiner box, you're probably going in with a single feed, all the strings on a single power point tracker. When you're going right into the inverter, you're likely using their multiple power point tracker options. And that's really beneficial for in-a-row shading, shade from trees, leaves, any debris or things that fall on the leaves, fall on the panels like leaves, that the PowerPoint trackers really help isolate those mismatch losses to just a string or two and doesn't affect the other strings that are on other MPPTs. So you might be able to squeeze out a tiny bit more energy out of your system by having those multiple MPPTs in use. Some of the downsides to this arrangement is, well, first, the communications that you want to run to these inverters just how you're running the long AC cables to each of these, now you got to run monitoring to each one and between each inverter. So if you have these mounted on the back or sides of each row, it's up and down, go underground to the next one and up, underground to the next one and back up. And that's a lot of time and money to install all those communication circuits, those long distances. So that's why I consider this a con in this particular arrangement. Mm-hmm. Also, operations and maintenance. I had an O&M company for many years, so this item is close to my heart. But when you have this equipment spread all throughout the array, the technicians need to walk a lot more from piece of equipment to piece of equipment. And those minutes really start to add up. The larger you make the site, then all of a sudden those minutes walking start to become hours. And that starts to take longer to do your maintenance, your troubleshooting. That's eventually going to start causing your O&M prices to start creeping up as it takes technicians longer to do everything. So you got to watch out for that with this layout. Voltage drop percentage. So of course with voltage drop, we have two sides to it. We have the DC voltage drop and we have the AC voltage drop. While we may be reducing the DC here, we have the AC that's either at 480 or 600 volts. That's going to be the longer run, which is lower than the DC voltage of 1,000 or 1,500. So you're probably going to have to do some more work to keep the overall DC and AC voltage drops effects, keep them to a minimum or within an acceptable tolerance. So those lower voltage of the 40 and 600 volts means you just need to upsize those cables probably a little bit more for those long distances.
Does that end up being like one of the major design constraints for this in terms of like the AC cables having to be upsized so much to account for the AC voltage drop?
It's one of many factors. I would say there's probably a handful that are all equally important, and that is certainly one. Conductors are one of those things that are one of the more expensive items on a project that you can actually control. There's a lot of pieces as an engineer or designer that we can't change. We got the inverter, but we can't really tweak that inverter or the panels or the switchboard. We could do minor things, but an area where we can really value engineer a system and really put our own individual stamp on it is through these conductor sizing and trying to figure out what is the best way to get the best bang for the buck of spending money on conductors, but making sure whatever we spend that additional money on, it's going to be paid for by reduced voltage drop. So it is an important area and a fun one for our engineers to work on because we can really have some flexibility in what we do.
Yeah.
I'm kind of curious, Rick, on you mentioned this is somewhat the default system configuration that we're seeing, and we're seeing that a lot as well on our side. I'm just curious if you get any of your clients, is this their preferred method, or is this kind of like the way that we've always done it, so that's why we're going to do it again? And I know we're going to talk about the other methods here in a minute, but just curious if you've ever gotten any pushback, I guess, on suggestions for changing this method.
Yeah. It wasn't really external pressure pushing us to do it. We just realized through doing just so many projects, so many iterations of design, that there were better ways to lay it out. But you're correct that a majority of our clients would come with this as their default, and they might give us their initial layout and say, all right, now run with this design and give us a permit set and construction set. And my engineers would be having conversations all the time. And, initially they're like, that sounds good, but I'm not quite sure yet. Just stick with this one for another project or two. But we kept just trying to consult them, tell them the pros and cons, and eventually most would come around and start adapting the other methods. But it's, I could understand that it could be, a little uncomfortable to do something that is a little less traditional in certain people's minds. And that right there is the main reason why I wrote this article. We've been having these conversations internally with our clients for several years now, but it just got to the point where like we're spending so much time talking about it. Maybe let's put together an article that just concisely has everything. And now we can just start sending it to our clients proactively and save some time. And I think that's really helped out over the last month or so since we released it.
Great. Yeah.
Yeah, that's great. So before I have a follow-up question, but maybe let's get into the alternative design. So you mentioned there is a different way of doing it, which is treating this more as a virtual. So why don't we get into that next example?
Okay, so this is very similar to the previous one, still no combiner boxes, but we're taking the inverters and taking from spread out through the array and pulling them all together in one spot. Maybe it's still right immediately adjacent to the array, or maybe it's off a little further out. Depends on the site, of course. So this has some of the same pros and cons as the previous, but a few things changed as well. If we want to go to the next slide. Yeah. So what was a con in the previous was running the communication, these long distance between inverters spread all over. Now, if you take those inverters and you got them all next to each other on the same pad or on the same rack, now the monitoring probably doesn't even need to go underground. Those communication circuits can just go and hit daisy chain these inverters that are right next to each other, just spaced as far apart as needed for ventilation. And it's much easier to install, as well as the O&M. The O&M makes it easier. So if you need to do any sort of testing, commissioning, recommissioning, troubleshooting, majority of work now is going to be done right here at the pad where all the inverters are at. And you don't need to go walking from inverter to inverter. Even simple things like opening them up. You know, you got to go open them all up. Then you go back and do all your tests, and you got to go back and close them all up. Lots of walking and lots of trips all around. This makes that a lot easier from the O&M standpoint. And also if you ever have to replace these inverters from the O&M standpoint, you know, these sites often get muddy and they don't always have good roads or even stone paths leading to the locations of inverters when they're spread throughout the array. But when you have all the inverters at a central location, it's very likely you've got a good access road there. So you can drive the vans or the trucks right up to it. It's a lot easier than to swap it out, any inverters or any equipment, without having to drive the trucks that like to get stuck out in these fields when you have to start driving around to all the different locations. So that's a few of the aspects that really help from the O&M standpoint. And another factor that comes into it is you start to get what we call free voltage drop. So that has to do with once an inverter starts clipping, that the voltage drop really doesn't matter. And we'll dive into this a little bit more in a few slides. I'll just give a quick 30-second summary right now. So yeah, in this case, we're increasing the DC voltage drop and decreasing, we're decreasing DC and increasing the DC and reducing the AC voltage drop. And that's a pretty good trade-off for a few reasons. First is the DC conductor cost is, it's easier to manage voltage drop at a higher voltage. So if these are at 1,000 or the 1,500 volts, as compared to the AC voltage, you're not going to experience quite as much voltage drop. So you can maintain that in the first side. But then with the free voltage drop, once you start clipping, that means really you have more DC power than your inverters can output to convert to AC and output. If you have more DC than you can use, then it doesn't really matter if you're starting to lose some DC from voltage drop losses. So that's why we start to say, oh, it's free. It doesn't cost you anything at that point once you're clipping. And we'll come back to that concept in a minute. But to getting to some of the cons to this particular layout is the conductor costs. I did say a moment ago that it's a little easier to manage the voltage drop on the DC side because of the higher voltage. However, These DC strings are likely in copper. They're number 10 or number 8 and or even number 12, and they're copper. They're not aluminum at that size. So they do get a little bit more expensive, where when we talk about combiner boxes, you can output with aluminum. That's a lot more cost effective than running all these small copper cables that could drive up the price a bit. And a con here is, oh, actually, no, this is not quite right, but this, you still have the multiple PowerPoint trackers here that you get the leverage. So that's a benefit.
So yes, you're actually getting the benefit of multiple PowerPoint trackers in those individual inverters.
Correct.
Yeah.
Without, wait, so can you go back to the previous slide?
Previous?
Yeah, so with combiners. Oh wait, the pros and cons with combiners.
That's last. That's the next one.
Oh, that's the next one.
Yep.
Sorry, have you gotten to that one already?
Nope.
Never mind. Okay, I still have another question in terms of central inverters, but maybe that will come up with the next one.
Okay.
All right.
Yeah, we can go to the next one. So this is the virtual central with combiner boxes. So the inverters and all the AC equipment is in the same location, but we're adding combiner boxes. So instead of running those individual strings that long distance to the inverter, we're now going to have the combiner boxes that are distributed throughout the array, and you have them at the end of the rows. So your small gauge DC strings that are in copper only run a short distance. And then out of the combiner boxes, we can come out with aluminum conductors, larger gauge, 1 or 2 big feeders instead, and run them all the way to the inverters. So some of the pros and cons to this one is it's got some of the same pros as the previous. The communications is still easy to install because the inverters are at that single pad. O&M is also can be easier. Not quite as much when you were having all the string level testing. We're at the inverters. Now you still have a little bit that you got to go out to the combiner boxes, but you don't really replace combiner boxes often. The string inverters are much more frequent. So being able to access those with your vehicle easier and have them more centralized for most of your maintenance that's in the inverters is still easier. With the long DC runs, you still have that free voltage drop benefit that we'll dive into some more in a few minutes. And big benefit compared to the previous is saving with the aluminum conductors now between the combiner box and the inverters. Some of the cons to this approach is that now you got to reintroduce those combiner boxes. Previously, we didn't have to spend the money on those. And the 1500 volt combiner boxes, they get up there in price. 1000 is a little more reasonable, but those 1500 volt ones get up in price. So you do got to add them back in, but usually you still make up for the cost of that by switching to the aluminum for that long run, more than makes up for that DC combiner cost.
And I think that's probably a point worth just talking about just a little bit, the aluminum versus the copper there. And by making that transition by the source circuits, which are going to be copper conductors, using those combiner boxes, that gives you an opportunity there to transition over to the aluminum in an effective manner. So that's definitely something that we're seeing a lot more of, use of aluminum conductors when you can make that transition on a lot of inverter output circuits as well, using aluminum. And of course, there's always have to look at everything, all the components you're using when you're using the aluminum conductors, but we're seeing that a lot more and more. And I don't know if that's true for what you guys are engineering and seeing, Rick.
Yeah. Marvin Hammond always likes to talk about aluminum conductors. He always gets mad when people are like, oh, I'm concerned about aluminum. I hear that they're more risky than copper. And as always saying, those are things from decades ago when aluminum first came out, and there were fires decades ago. But the modern aluminum alloy conductors are really well made and don't have a lot of the issues that people think they do at the terminations, and and working with them and bending them. You do want to be a little more careful when you're cutting away the insulation, not to nick it. But as long as you do that and have good workmanship, aluminum conductors are still great. And if anyone that's concerned about that is probably concerned about old news and not the modern aluminum conductors.
It's funny how that's persisted through us. I think there was like house fires in the 70s or something, and aluminum wire got the blame, but it really wasn't even the aluminum wire that was the cause. But that does still seem to persist.
Mm-hmm. Yep. Well, and that actually came up as a question from someone in our audience member, was why does the industry still go with copper and not aluminum? So it sounds like you just addressed some of those things, but I guess they're still used for the lower gauge, I guess lower voltage stuff. But when you get into higher and you have long enough runs, is that where it mainly makes sense to make that transition?
Yeah, as you have the conductor sizes as they go up, that the difference in price between copper and aluminum spreads. So as you start going from like a number 10 to then several sizes more to 2 to 250 all the way up to 500, that delta in pricing increases almost exponentially in what it takes to replace copper for aluminum. So when you have the opportunity to use aluminum, we really try to push for that. And most of the time it is accepted by our clients and they're okay with it. Some have some initial pushback, but once they see the price difference, or they send to their contractor and say, "Oh, give me the two prices," and they see the price of aluminum, they're like, "Oh, that's too good to pass up." So risk reward, and like we said, the risk isn't really there; it's more perceived risk. So.
Mm-hmm. We have another question that just came in from our audience, from Drew Cates. Thanks for joining us today, Drew. He's asking, is it safe to assume that all combiner OEMs include lugs that are rated for 90 degrees Celsius aluminum conductors? Maybe that's a question you can answer, Ryan.
So the 90C, I guess, is the question. I would say all of the combiners I've seen are rated for aluminum conductors. 75 versus 90 would be the question on the rating on those terminals. And then, a big part of that too is what's connected to the terminals. If there's overcurrent devices connected to them, or if they're just straight lugs, that will have a big impact on what that 90 degrees C versus 75 C. So I would say it's I wouldn't say assume anything, but I think it would be a safe expectation that you would have at least 75C conductor terminals rated for aluminum conductors.
Mm-hmm.
Yep. Yeah, Ryan, you're spot on. It's all about that terminal rating is the questionable part about that question. If you have mechanical lugs, that's what the set screw that pinches down, that's likely 75. But if you want to get the 90-degree terminals, then you're probably going to need to go to the compression lug, where it's not the set screw. That's where you need to have the hydraulic crimper that crimps around it. And then you land it on a stud and bolt it on. That's going to be needed to get to the 90-degree terminals. And then the 90-degree ampacity to take advantage. So you can spec inverters to take advantage of that. But you just need to make sure you spec. You won't be able to get that 90-degree rating if it's a mechanical lug. So those mechanical lugs, like Ryan said, are very likely going to be both copper and aluminum rated, but only 75C and not the 90.
Mm-hmm. We have another question coming in from the audience. What about increased O&M of aluminum at the terminations? Is there an issue of retorquing over time?
Oh, so that's a whole nother can of worms. So the retorquing is something you want to be careful about. And the problems that we've seen from my years in O&M is more from over torquing. If you go and look at the UL listing in most of these lugs, they say you torque it once and you leave it. And you're not supposed to keep torquing and retorquing as the threads settle, that you want to hit it with an IR gun. And If the thermal imaging shows that's starting to overheat, then you probably want to retorque it again. But if you're just going every year and you just keep retorquing, you're going to start to keep damaging and deforming those conductors and becoming a bigger problem. So, and an aluminum is a softer metal. So if you're going to keep retorquing, that problem would be worse than with copper. So I wouldn't necessarily say the issue is with copper versus aluminum as much as that practice in O&M might need to change. Torque it once and don't torque it again unless the thermal imaging shows that it's an issue.
Mm-hmm. All right. So this next question that came in from the audience, from Adesola, and I'm going to butcher this name. I'm so sorry. Adesola Adeniyi. Which one is the better approach of the sample shown on the free voltage drop? So this kind of ties into the next topic of this conversation, which is starting to talk about free voltage drop and what that means. So Rick, you wrote an article about this as well on, I believe, the Pure Power Engineering blog on the website. So I think Lucas will be putting a link to that blog post within our chat so you guys can read through that. But talk to me about this concept of free voltage drop. What do you mean by that, Rick?
Sure. So to get into the details, it's really complicated, but it's kind of easy to say the surface level. It's just the details then really are a slippery slope of complexity. So we'll start with the simple side of it. And here you can kind of see the two different graphs here about what your voltage drop losses would be, and in the green in each. So on the left, you have at 1%. So you can see during this day, the sunny day, what the voltage drop losses would be at 1%. And compared to the right, if you have a much higher voltage drop, 5%, it would be no surprise that you're losing a lot more. That green are losses if you were not clipping. But once you start clipping, then all that area in the green becomes that free voltage drop, and you no longer experience it because, like I mentioned earlier, you already have more DC power than you can use and convert to AC. So the fact that you're losing a little bit more from voltage drop doesn't matter. So you can see you might spend a bunch of money in your contract saying, my contract says I have to be at 1% voltage drop. And you can see in this case that a lot of that benefit is gained on the left. You do gain it below that clipping line on the shoulders at the start and end of the day before you're clipping. So you still get some benefit there versus on the right, that 5% voltage drop has those lines in the red that you can see a little bit better. So you still have voltage drop when you're not clipping, and that's a little bit more. But the higher that DC to AC ratio becomes, the more frequently you're going to be in that clipping area, and the more frequently this voltage drop will start to become free and not cost you anything. And so, like I was mentioning, if the contract has a particular limit to voltage drop that contractually kind of seems arbitrary, 1% or 2%, if you have a high DC to AC ratio, that you might spend a lot of money on conductors trying to get to this 1% voltage drop where it's never going to pay back, because all you're doing by saving is those little bits on the shoulder at the start and end of the day, or in the middle of the day where it's like clouds pass when you're not at full output of the inverters. So it becomes really difficult to start to get a return on that investment of upsizing the conductors. If you start realizing that and saying, oh, well, why drive the voltage drop down so low? Let me just accept some and optimize it more for performance rather than just voltage drop. Then you can really start to drive the cost down of the installed system, drive down the CapEx, while having a negligible effect on the energy output. There's still some, but the savings that you get on the CapEx are usually much more than the lifetime gain you would get from driving down voltage drop.
Mm-hmm. And so here we're specifically talking about the DC side, right?
Yes.
Okay.
That's an important distinction, because this only applies on the DC side because of clipping. Once it gets to AC, then it is very important to minimize that AC voltage drop because there is no free thing. Every little bit of power loss from voltage drop is gone forever. It doesn't matter if you're clipping or not. So that's one of the benefits by sliding the inverters close to the switchboard, the panel board, the switchgear, transformer. You minimize those AC distances, knowing that you can never reclaim or recapture any of that. Minimize that, and then have the longer DC runs where, especially if you have this high DC to AC ratio that you'll be clipping, you have plenty of extra power to cross those longer distances.
Right, and I think it's probably worth pointing out too, not just on the AC side, the losses that you're seeing, but also the longer runs on the AC side the losses will equate to voltage rise at the inverter, which could then, the inverters could trip off out of their windows, their specs. And so, if the inverter's not operating, you're losing everything. And so it becomes an even bigger, I guess, issue or something that you have to look at in terms of the design when you're looking at the design side of that. So,
yep.
Mm-hmm. So is from 1500 volts to 1000 volts, how does the concept of free voltage drop change?
Yeah, so the concept is still the same, that if you're clipping at whatever voltage, if you have more power, then you have that spare DC power and voltage drop. Maybe if you're at 1000 volts, you have a little bit higher voltage drop to begin with. The lower the voltage, the higher the voltage drop. At 1500 volts, it's almost like it's easier to maintain. So you might not have to work so hard to drop that voltage. So in a way, you could say that at 1000 volts, the concept of free voltage drop is actually more so than at 1500 volts.
So is there, and this question came in from Paul Krem for our audience. Thanks for joining us today, Paul. Is there a recommended method for quantifying the effective voltage drop percentage, accounting for free voltage drop when clipping? So i.e., if you calculate 5% voltage drop, but effectively see only 2% DC voltage drop. So it sounds like you basically have to run through the calculation, right?
Yeah, well, there's two equations. First, you calculate what the voltage drop would be at STC, and then you take that and you put it in the PV syst, and then you run it for that. So you can run a few different iterations of calculations, calculating conductor size and voltage drops, and then take that and put it into PV syst to figure out what it then is the energy gain or loss that you would get from the different design parameters.
Yeah, and so to mention, we had done a paper a while ago on voltage drop specifically, not getting into free voltage drop, but essentially there's the voltage drop that you have, but then what we're really concerned about and what you're showing here, Rick, is the energy production, and that's ultimately what we're getting paid for is the kilowatt hours. And so you want to take that voltage drop and equate that into what does that do to your energy production over the life of this, or over a year, month life of the system, and able to quantify that. And so I think in short, kind of what you were saying there, Rick, is you do your math, figure out what it is, and then you have to do the modeling to figure out what the real effective loss is.
Yep. True.
And we have that blog article on our website. So maybe, Lucas, if you could put the link to that article in the chat, if you want to read up more about that, the difference between, STC voltage drop versus, effective voltage drop. So let's keep going. Do we have another slide beyond this, or is this the last one for the voltage drop one? We have one more. So what are we looking at here?
This is just showing the different DC to AC ratios, where the previous one was showing different voltage drop levels. Mm-hmm. This is assuming the same voltage drop percentage, which I don't recall what that was, but it's the different DC to AC ratio, 1.5 versus a 1.2. And once again, the area in the green is that free voltage drop that you can get. And obviously the higher DC to AC ratio has more green to it. Also looking below the line is important too, though, because that is the voltage drop that does start the cost. But you can see that you can barely see in both of these the red sliver. That's because it is pretty small, because we're saying at STC, if you're at 2% STC, that's full output or more or less. All these levels below clipping are not at STC, and your voltage drop really drops quickly below there. Actually exponentially decreases. So you have a lot less voltage drop down low. Voltage drop is a bigger issue at the higher levels of output. But if you have a high DC to AC ratio, you never really get to there because you start clipping. So this is just showing the difference in the green, and that the higher DC to AC ratio really starts to drive more and more of this free voltage drop. If you have a really low DC to AC ratio, then you have a minimal amount of it. And you probably do want to think about spending the money on upsizing the conductors, because you might get that return on the investment, since you are really experiencing it most times of the day.
Mm-hmm. Yeah, so with knowing that at the higher DC to AC ratio is when I guess you start seeing this free voltage drop, what is the trade-off in terms of installation costs versus energy production?
Well, it's really about assuming that your array, it takes up the size of the field that it is. It's how much inverters do you really need to. So by doing a higher DC to AC ratio, you're trying to get away with fewer inverters, fewer kW of inverters. So saving money on the price of the inverters, the price of the installation and wiring to the inverters, the monitoring, the ongoing monitoring costs of the inverters, ongoing O&M to service each one. So it's more about trying to eliminate the amount of inverters and all the savings that come along with that.
Mm-hmm. Excellent. And to kind of tie this back to our audience question earlier in terms of, what's the better layout of looking at that, back to the 1500 volt design considerations of if you're going to run your AC conductors longer or your DC conductors longer, which one is the better design option? And maybe Ryan, you could answer this. Do you want to go back to that slide and maybe we can look at that? Layout.
One of these layouts?
Yeah.
Yeah, so I think that's a question that comes up a fair amount. It used to come up a lot. And, as Rick was talking about the DC voltage drop, you have a lot more, I would say, play with, or you have a lot more flexibility with being able to run the DC conductors a further distance. And a big part of it is most of our systems are going to be, so, in a ground mount system, utilizing 1500 volt inverters, 1500 volt arrays. And so your voltage is already much higher than what the output of the inverter is going to be, either at 600 volts or 480 volts. And so you have a lot more voltage to begin with, and then you also have the ability to, what we just went through with the free voltage drop, but then also because the inverters have, on the AC output side, they have a much narrower AC operating window. You have to stay within that. And so it becomes really important to make sure that you're really, really paying attention to that. And so that can become a big problem. So long answer for, which do you run longer, AC or DC, all things being equal. And of course, all things are never equal, but the DC would be the first choice to look at how you can run that the longer distance when you're talking purely the performance of the system.
Mm-hmm. And this question came from Michael Palmer with Megger. Is there any end to the end of ever increasing voltage in large scale arrays, or is it all about saving money on cable runs?
Is that asking why not keep increasing voltage from 1015 to 2000 and above?
Yeah, that's sounding like, why are we, is it going to keep going above 1500 volts?
Yeah, I mean, there's a handful of factors. First, the safety. So the higher you get the voltage, the greater risk you put the technicians that are out there working. So there is a limit to that. And the limit is, number one, driven by safety. And that's what the National Electrical Code is primarily about, is safe installations. There is then a technological portion to it that, if you're going to start increasing the voltage, you need to make sure you have the equipment to do that. And if you're going to start going to 2000 volt DC system, your first challenge is going to be, well, what's the AC output of that? You already see that at the 1500 volt, most of the inverters are outputting 600 volt, not 480. So you need to get 600 volt AC, panel boards, switchboards, etc. If you go to 2000, you're probably not even going to stick at that 600. You're going to have to go to 1000 volt AC. Now you're in medium voltage kind of land over. A lot of the gear that's rated for 600 is no longer rated for that. So you got to start looking into the gear challenges with that. Real quick, the reason why is with the power electronics, and this will probably improve in a few years, but the power electronics can only make a jump from that DC voltage to AC of a certain amount. You can't just, and still be cost effective. So going from, like the 2000 to 480 is going to be really expensive to build that way, to do such a big jump from 2000 to 480. It's no problem from 1000 to 480, or even 1500 volts to the 600. There's a few inverters out there that'll do the 1500 volt to 480, but they're also on the a little smaller on the kW side. So like I said, there's the technology equipment challenge to increasing voltage, but number one is really just the safety for the workers.
Mm-hmm.
And code does address that too, in a sense where, we can't do more than 1000. Well, 600 volts is our maximum voltage on residential 1 and 2 family dwellings. Then we go up to 1000 volts on all other buildings, and we're essentially capped at 1000 volts DC on buildings for our circuit conductors. So the 1500 volts really even only comes into play on our ground mount systems, but for all the reasons why Rick was stating, it's, we're effectively stuck there for a little while.
Mm-hmm. So going back to some of the 1500 volt design considerations again, how do you deal with arc fault protection when using combiner boxes ahead of the string inverter?
Sure. Well, two different answers for the 1000 or 1500 volt. If you're at 1000, you've got the combiner boxes that are available in that voltage that you can get the arc fault circuit detection and interruption. When it comes to the 1500 volt, then that becomes a challenge, not just in the combiner box, but the inverters themselves as well, that there is extremely limited products out there, if any at all, really. We struggle to find any. Last year, there was one manufacturer making a combiner box with 1500 volt AFCI, but they stopped providing them. So they probably ran into some technological issues. But you just, it's not really available. So you can rely on other areas of the code to not, to get around that, such as 90.4.
Right. So you mentioned that a lot of your clients are still inclined to do distributed string inverter design layouts just because that's what they're familiar with, they're more comfortable. I'm curious, is there still also, I imagine a lot of companies are still also using actual central inverters rather than string inverters. Are you seeing that as a transition more and more, or a shift more and more of using string inverters in that virtual central layout? And maybe Ryan, if we could go back to that slide, what are your thoughts on that in terms of, what the trend is, and then why some people are inclined to make that switch and some people aren't?
Yeah. So when you have that debate, do I go with the virtual central with string inverters, which is versus an actual central inverter? Over the last 5 years, that argument keeps changing. Really, that line where you say 5 years ago, oh, anything above a megawatt should still be central, and then a year later, anything above 1.5 should be a true central. And now you're getting up around 2 or 3 or 4 megawatt blocks that now you're saying, oh, well, string inverters are now better for that. So that line between where you would say, oh, let's use the string inverters in a virtual central versus an actual central, that keeps going up in size for those megawatt blocks.
Yeah, and I would imagine that it's also creates smaller building blocks, right? So if you have a central inverter, then you're basically at the mercy of the building block of that particular size of inverter, versus being able to take a lot smaller string inverters and use however many you need to make the system size that you want.
Yeah, you can probably more fit even each array if they're slightly different sizes, because a lot of these mid-size utility scale projects don't have nice, neat, every array is a perfect rectangle of the same size. They're all these wacky shapes that go with the site. So being able to slightly do different size virtual centrals for each subarray is a benefit. Of course, the debate of string versus central is a whole nother hour-long topic we'll have to do next.
Yeah. What is there, I guess, a kind of max range that you would recommend, or that you would say, like, okay, for up to, 2 megawatts or 3 or whatever the system size is, that you would recommend if a client asked, which way should I go, you would recommend virtual string?
Sure. At this point, I don't think it's about system size as much as the type of client and what they're doing for the O&M. If it's large enough and the project has a full-time technician on there 5 days a week, and you've got lots of spare parts for the central inverter there that's already, then maybe you can get that central inverter up and running faster. But if you're a typical C&I developer that's going in and doing a lot of these community solar projects that are 5-10 megawatts, you probably have a third-party O&M company, or doing it yourself. You don't have as fast a turnaround on repairs. You probably don't have all the spare parts you need. Then I'd say that string inverters are better, because then you can just pull one string inverter off and put the next one on. Oh, that brand and model isn't available anymore. It's 2 years old. No problem. Just fit a new one up there, and it's a lot more modular and works a little bit better. So for me, it's now reached a point where it's less about system size and more about the type of client and the type of O&M that you're capable of doing between string inverters and central inverter.
Yeah, that makes a lot of sense. Really taking a holistic approach around it and seeing what all the pros and cons are. Excellent. Well, we are approaching the end of the hour, and I just wanted to take a moment to thank you so much, Rick, for all of your insights and sharing this great information with us and our audience. We are happy to have you on here.
Yeah, I love to talk technical and nerd out on these topics.
Yeah. And we're looking forward. I think we're going to have Marvin from your team on in a future month. So that'll be exciting. We'll get to chat with him some more. And Ryan, if you could go to some of the later slides. I did want to share with our audience, solar and storage has been such a confusing and hot topic lately, especially around design, that we have started offering solar plus storage workshops this year. So we will be teaching those. Actually, Justine Sanchez, who has been in the industry for over 20 years and teaches at SEI and has put together these courses for Mayfield Renewables, and is good for NABCEP credit, but she'll be going through the actual codes for ESS and then all of the topics that you see there. So if you're interested in that, reach out to us. They will be rotating, so throughout the quarter. Right now we're offering a 15% discount, and I think there are links being shared in the chat right now. And if we didn't get to all your questions, I apologize. Feel free to reach out to us. Our contact info is up on the screen. You can also email me at technical@mayfield.energy. And definitely check out our previous AMAs. We're going to send out, this whole thing was recorded, so we'll send out a follow-up email with the recording of this. And if you want to check out any of our previous AMAs, they're up on our website. And our next one will be at the end of next month. So that is all we have for today, unless you guys had any additional comments or things that you wanted to go over.
No, I think like Rick was saying, I could probably nerd out and talk about all this stuff for a lot longer, and there's topics we could spend even more time on. But really appreciate your time, Rick. This is great. Love having you on and all the insight you have.
Thank you very much. It's been great talking with you guys for the last few weeks about this and the other things that we work on together.
Yeah.
Wonderful.
Excellent. Well, have a great rest of your day, and we'll hopefully see you again next time.
Great. Thanks.
Thank you.